The influence of observation in quantum physics. Among the most intriguing and puzzling aspects of quantum mechanics is a phenomenon that has stirred both awe and confusion: the observation effect. This principle proposes that simply observing a system can fundamentally alter its behavior. Initially, this might appear counterintuitive. How could merely looking at something change its inherent nature? The answer lies deep within the baffling and non-intuitive structure of quantum theory, where measurement doesn't merely detect a condition, it actively helps define it. Let's begin with a relatable analogy. Imagine you're checking the temperature of a hot beverage. You insert a thermometer into your coffee and get a reading. In doing so, the thermometer reveals the temperature without significantly changing it. It seems natural to assume that all forms of measurement operate in this passive, neutral manner. However, within the quantum realm, this assumption collapses. In this domain, the act of measuring can dramatically influence the system being analyzed. The observation effect is closely tied to the idea of superposition. In quantum theory, particles do not possess definite attributes until they are observed. Rather, they exist in a superimposed state, a fusion of all potential configurations. Take, for example, an electron in orbit around an atomic nucleus. Classical physics might expect it to follow a predictable path, but quantum physics describes it as existing in a probabilistic haze, occupying multiple positions, velocities, and spin states simultaneously. Only upon measurement does this haze collapse into a single defined outcome. This implies that observation doesn't simply reveal the current state of a quantum entity, it plays a role in determining that state. A legendary demonstration of this principle is the double-slit experiment, a foundational concept in quantum mechanics. Picture a barrier with two openings, behind which stands a detection screen. When electrons are fired at the barrier without monitoring which slit they pass through, they behave like waves, creating an interference pattern, suggesting that each electron travels through both slits simultaneously and interferes with itself. However, when a device is placed to determine which slit the electron uses, this wave behavior vanishes. The electrons now act like individual particles, striking the screen in distinct locations. This dramatic shift in behavior, brought about solely by observation, is the core of the observation effect. This leads to profound philosophical implications. If observing a particle changes its behavior, what does that imply about the nature of the universe? Some thinkers argue that reality itself might not be well defined until it is observed. This radically contrasts with our everyday perception, in which objects like trees or vehicles appear to exist independently of our attention. But in the quantum landscape, entities dwell in a realm of potential states, only crystallizing into specific realities upon observation. This observation effect, therefore, compels us to reconsider the foundation of what we call reality. Could it be that existence is fundamentally a web of probabilities, waiting for consciousness to transform it into something concrete? One of the most famous quotes reflecting this dilemma comes from Niels Bohr. Everything we call real is made of things that cannot be regarded as real. Bohr was highlighting the peculiar, probabilistic essence of the quantum domain. While our daily experiences suggest stable, well-defined objects, a red apple, a four-legged chair, quantum physics reveals a world that is fluid, dynamic, and uncertain at its base. This brings us to a deeper question. What role does the observer play in the cosmos? One provocative theory is John Archibald Wheeler's participatory universe. Wheeler posited that the cosmos is not a fixed, pre-existing structure, but one that is influenced, perhaps even brought into being, by observation. This doesn't imply the universe disappears when unobserved, but it suggests that how we perceive it might shape its properties. Wheeler's theory aligns with a growing perspective in quantum theory and philosophy that consciousness might be fundamental to physical reality. According to this view, our measurements of quantum systems
are not merely passive acts, but potentially formative ones. Some researchers go further, suggesting that human consciousness itself may participate in generating the physical world we experience.
Not everyone agrees with this interpretation. A significant number of scientists believe the observation effect can be explained without invoking consciousness. They argue it results from the unavoidable disturbance that any measurement causes. For instance, in the double-slit experiment, even without human awareness, the presence of a detector interacting with the particle is enough to change its behavior. From this standpoint, the issue lies not in the act of conscious observation, but in the physical interaction during measurement. Regardless of which interpretation one adopts, the observation effect has significant consequences for how we understand quantum systems and, by extension, reality. It demonstrates that, at the tiniest scales, the boundaries between observer and observed are far more porous than classical physics assumed. This is not a minor technicality, but a foundational transformation in our comprehension of existence. In practical terms, the observation effect also plays a crucial role in emerging technologies. Quantum computing, a revolutionary area of innovation, relies on quantum principles such as superposition and entanglement to carry out complex calculations far beyond the reach of conventional machines. However, the observation effect creates a challenge here. Retrieving information from a quantum system requires measurement, which inevitably disrupts the quantum state, collapsing its superposition. This makes managing quantum states without losing valuable data a central hurdle in quantum computing. Similarly, quantum cryptography benefits from the observation effect. It leverages the fact that any attempt to intercept quantum communication will disturb the system, signaling unauthorized access. This makes quantum-based encryption incredibly secure, far more so than traditional methods. In this way, the observation effect is not merely a theoretical puzzle. It has concrete, real-world applications that are reshaping how we compute, communicate, and think about security. It also forces us to reevaluate the connection between ourselves and the universe. Whether we're probing the mysteries of consciousness, studying the structure of the cosmos, or designing the next generation of technology, the observation effect reminds us that the act of perception is never neutral. The quantum realm teaches us that the line between observer and observed is not just blurred, it may be altogether illusory. In this strange domain, our interactions with the world alter its very fabric, hinting at a universe that is more mysterious and interconnected than we ever imagined. The enigma of quantum entanglement. Quantum entanglement stands as one of the most astonishing and perplexing ideas in contemporary physics. It's so baffling that it often appears to contradict logic and everyday reasoning. Picture a pair of particles, such as electrons, formed in such a manner that their characteristics become intrinsically connected, no matter the physical distance between them. Once entangled, these particles exchange information in a way that defies the principles of classical physics. It's as if the state of one particle instantly determines the state of its twin, even if separated by vast cosmic distances. To unravel this peculiar effect, we must enter the unconventional world of quantum physics. In the quantum domain, particles don't act like solid, tangible entities. Instead, they exist in probabilistic states, with their properties becoming fixed only upon measurement. This is a stark departure from the stable and predictable objects like chairs or cars we encounter in our daily existence. In the quantum realm, particles remain in multiple potential states simultaneously, a phenomenon known as superposition. This foundational concept of quantum theory allows a particle to occupy various conditions at once until we observe it. Now, imagine two electrons that are entangled. Before measurement, both exist in superpositions of several possible configurations. When you observe one and determine, for instance, its spin, a fundamental trait, the state of the other is instantly fixed, regardless of distance. This behavior suggests a mysterious link that instantaneously connects them, even if one is on Earth and the other is light years away. This is the essence of quantum entanglement. Albert Einstein famously criticized this notion, dubbing it spooky action at a distance. He found the implications deeply unsettling. According to relativity, no signal or information should travel faster than the speed of light. Yet, entanglement seems to defy that very limit. Einstein wasn't the only one with reservations. Niels Bohr, another quantum pioneer, was heavily engaged in exploring the consequences of this bizarre interaction. Despite skepticism, experimental evidence has consistently upheld entanglement as a real phenomenon. In the 1960s, physicist John Bell formulated Bell's theorem, which provided a method to empirically test the quantum predictions involving entanglement. According to Bell's work, if quantum mechanics were accurate, then entangled particles would violate specific inequalities rooted in classical expectations. Subsequent experiments, most notably those conducted by Alan Aspect in the 1980s, validated these predictions. Entangled particles did indeed breach classical constraints, confirming that entanglement is not a mere theoretical oddity, but an observable fact. So, what are we to make of this phenomenon? Why do entangled particles behave this way? And how can we possibly interpret it? One viewpoint is that entanglement doesn't involve faster than light communication at all. Rather, it reflects a profound holistic relationship between the particles, one that transcends conventional notions of space and time. Instead of imagining particles as standalone units, this perspective sees them as components of an interconnected quantum system. This challenges classical physics' idea of separateness and prompts us to reconceptualize the universe as a deeply entangled whole. A helpful metaphor is the classic glove analogy. Suppose you have one left-hand glove and one right-hand glove, and you place them in separate boxes. If you send one box to Paris and the other to Tokyo, and then open the Paris box to find a left glove, you instantly know the Tokyo box contains the right one. However, the gloves were always determined. In quantum entanglement, the properties don't exist until measured, and it's this instant co-determination that sets it apart. The connection in the glove analogy represents classical correlation, but entanglement goes beyond that, entering a realm of quantum connectivity that we still don't fully understand. Moreover, entanglement doesn't just reshape our understanding of space and time, it also profoundly impacts how we think about information. In classical physics, data about a system is only obtained through measurement, and it's bounded by the speed of light. Entanglement, however, hints that information might bypass these limits. This has transformative implications, especially in cutting-edge technologies like quantum computing. Unlike traditional computers that use binary bits, quantum computers use qubits, quantum bits, that can be in several states at once due to superposition. This allows quantum machines to process enormous data sets simultaneously, offering tremendous computational potential. But what truly empowers quantum computing is entanglement. When qubits are entangled, they collaborate in ways impossible for classical bits. This enables quantum algorithms to solve problems that would take classical computers thousands of years. Entanglement also underpins innovations in quantum cryptography. In techniques like quantum key distribution, QKD, secure communication is guaranteed by the entangled state of particles. Any attempt to intercept or measure the entangled system disrupts it, immediately alerting the intended parties. This makes quantum encryption far more secure than traditional methods. Beyond practical use, entanglement raises philosophical and scientific questions about the very nature of existence. If particles can exhibit instantaneous links across cosmic distances, does that suggest the universe is far more unified than previously believed? Could hidden quantum connections exist throughout nature, pointing to an underlying structure yet to be unveiled? Might entanglement offer a path to a theory of everything, a framework that unites quantum mechanics with Einstein's general relativity? As our exploration of entanglement deepens, we confront not only perplexing behavior in particles, but also the limits of our current understanding of reality. Entanglement urges us to rethink the fabric of the cosmos, pushing us to expand the horizon of what we believe is possible. At its heart, quantum entanglement is more than just an academic curiosity. It offers a rare window into the quantum universe, a realm where classical laws dissolve and where the bizarre beauty of quantum rules reigns supreme. As research marches forward, we move ever closer to decoding the ultimate secrets of the cosmos and perhaps uncovering the deeper truths of existence itself. The essence of elementary particles. Elementary particles form the foundation of everything in existence, from minuscule grains of dust to the largest cosmic structures. Despite their significance, they remain remarkably elusive and complex to grasp. Their behavior defies the norms of everyday experience, making them difficult to conceptualize through classical thinking. To truly understand these particles, we must venture into the bizarre and counterintuitive domain of quantum physics. Fundamental particles are defined as the smallest units of matter that cannot be reduced into simpler components. Historically, atoms were once believed to be these indivisible units. However, advancements in physics unveiled that atoms themselves consist of even more minute constituents, particles that not only construct all known matter, but also govern the interactions across the universe. This narrative begins in the 1800s with John Dalton, who proposed that matter is made of tiny, indivisible entities he termed atoms. But scientific discoveries soon revealed the atom's internal complexity. In the early 1900s, work by J.J. Thomson, Ernest Rutherford, and Niels Bohr demonstrated that atoms consist of a dense core of protons and neutrons, orbited by electrons, marking the birth of subatomic physics. As experimental technology, such as particle accelerators, progressed, physicists identified particles even smaller than protons, neutrons, and electrons. These discoveries led to the formulation of the Standard Model of particle physics, a framework describing the essential particles and the forces influencing them. Within this model, particles are sorted into two main families, fermions and bosons. Fermions constitute matter, while bosons are the intermediaries of fundamental forces. Fermions adhere to the Pauli exclusion principle, which asserts that identical fermions cannot occupy the same quantum state at the same time. This group includes quarks and leptons, which serve as the foundational components of matter. Quarks are categorized into 6 kinds: up, down, charm, strange, top, and bottom. Similarly, leptons also come in 6 types: the electron, muon, tau, and their respective neutrinos. Quarks are never found alone. They bind together to form composite particles like protons and neutrons. Electrons, in contrast, are stable and orbit atomic nuclei, playing a central role in chemical processes. Quarks are bound together by the strong nuclear force, conveyed by particles known as gluons. This force operates intensely over very short ranges, ensuring that quarks remain confined within hadrons like protons and neutrons. Gluons, which have no mass, carry a unique property called color charge. This attribute determines how quarks interact, functioning similarly to electric charge but operating under the distinct rules of the strong force. Leptons do not interact via the strong force. Instead, they respond to the electromagnetic and weak nuclear forces. For example, electrons are influenced by electromagnetic forces, the same forces responsible for electricity and magnetism. Neutrinos, though difficult to detect due to their weak interactions, are subject to the weak force and play roles in processes such as radioactive decay. Despite their elusive nature, neutrinos are among the most abundant particles in existence. Bosons, unlike fermions, are responsible for transmitting forces between particles. The universe's 4 fundamental forces, gravity, electromagnetism, the strong force, and the weak force, are each associated with a different boson. The photon, for instance, carries the electromagnetic force. The weak force is mediated by the W and Z bosons, which govern processes like radioactive decay. Gluons, as previously mentioned, transmit the strong nuclear force. Another pivotal particle is the Higgs boson, discovered in 2012. It is tied to the Higgs field, which imparts mass to particles. The interaction between a particle and the Higgs field determines its mass. The stronger the interaction, the greater the mass. The Higgs boson's discovery at CERN marked a milestone in confirming the Standard Model's predictions and validating the existence of the Higgs field. Nevertheless, the Standard Model, while remarkably successful, does not provide a complete description of the universe. It fails to incorporate gravity, which is currently described by Einstein's theory of general relativity. Additionally, it cannot account for dark matter and dark energy, mysterious components that together comprise the majority of the universe's mass-energy content. The Standard Model also relies on input values such as particle masses, which are experimentally measured rather than derived from first principles. This has prompted ongoing efforts to find a more comprehensive theory that extends beyond the Standard Model. One such idea is string theory, which posits that fundamental particles are not point-like but rather tiny, vibrating one-dimensional strings. Different vibrational patterns of these strings represent different particles. If validated, string theory could offer a unified description of all known forces, including gravity. Another focus of contemporary research is neutrinos. These particles, once thought to be massless, have been found to possess tiny amounts of mass and rarely interact with matter. Every second, countless neutrinos pass through your body undetected. Unraveling their secrets could unlock new directions in particle physics. The quest to understand dark matter is also central to modern research. Though invisible, dark matter's gravitational pull reveals its presence. It's estimated to constitute roughly 27% of the universe. Some scientists hypothesize that dark matter is composed of unknown particles like WIMPs, weakly interacting massive particles. Identifying these could drastically reshape our understanding of the cosmos. As our exploration of fundamental particles continues, we are repeatedly pushed to reconsider our understanding of space, time, and the nature of existence. With each discovery, we learn how much more remains hidden. Are there unknown particles waiting to be detected? Could there be undiscovered forces shaping the universe? Ultimately, the study of elementary particles is about more than understanding matter. It is about uncovering the universe's most profound truths. By probing the smallest constituents of reality, we inch closer to understanding the structure of the cosmos, the forces that shape it, and the origin of everything within it. The pursuit is far from over, and every breakthrough brings us nearer to deciphering the ultimate mysteries of existence. The enigma of Schrödinger's cat. The Schrödinger's cat dilemma is among the most iconic conceptual puzzles in quantum physics, frequently employed to emphasize the strange and seemingly contradictory aspects of quantum theory. But what is its true significance? How does it disrupt our perception of existence? And why has it ignited ongoing discourse since its inception? At first, the concept of a feline simultaneously alive and dead appears ludicrous. Nevertheless, embedded within this scenario is a profound investigation into how observation affects reality, the influence of the observer, and the foundational structure of quantum phenomena. Erwin Schrödinger, a theoretical physicist from Austria, devised this mental illustration in 1935 to question the Copenhagen interpretation, then the prevailing framework of quantum physics. According to this viewpoint, quantum entities inhabit a superposed state, embodying multiple possibilities until observation collapses them into a specific outcome. Schrödinger's cat serves as a vehicle to probe the unsettling and perplexing ramifications of applying this framework to tangible macroscopic systems. Picture this hypothetical. A cat is enclosed within a sealed chamber containing a radioactive particle, a Geiger counter, a flask of lethal gas, and a mechanical hammer. This apparatus is arranged so that if the Geiger counter registers radioactive decay, a random quantum occurrence, it triggers the hammer to shatter the flask, releasing the poison and causing the cat's death. Conversely, if no decay is detected, the feline survives. Since the radioactive particle is governed by quantum indeterminacy, it occupies a dual state, both decayed and intact. Hence, by quantum principles, until the box is opened and the setup observed, the atom remains in this limbo, and consequently, the cat exists in a merged state, both living and deceased. This illustrates the core paradox. On the quantum level, particles such as photons and electrons can exist in overlapping conditions. This is known as superposition. But when these concepts are extended to organisms like cats, which clearly exist in distinct states, our usual sense of logic collapses. The notion of a creature both alive and dead simultaneously defies common experience, but quantum laws operate independently of our classical sensibilities. The essence of the cat paradox rests in quantum theory's interpretation. In the Copenhagen model, as long as no one observes the system, all potentialities coexist in a combined state. Only when a measurement takes place, e. when the box is opened and someone looks, does the wave function collapse, selecting a definite state. This wave function collapse, how and why a quantum system settles into one outcome, is among the most profound mysteries in physics. Prior to opening the box, the cat embodies a dual state. But this raises a crucial issue. How can a cat, a large and complex being, inhabit such a surreal quantum configuration? In the visible world, things are either dead or alive, not both. This contradiction suggests a deeper challenge in applying quantum mechanics to ordinary objects. One proposed solution is that superposition applies primarily to atomic scale phenomena. In contrast, large objects like cats consist of trillions of particles whose interactions with the surrounding environment lead to a process called decoherence. Decoherence refers to the collapse of superposition due to entanglement with environmental factors. This interaction compels the system to behave classically. In effect, while the atom might exist in overlapping states, the cat, being part of a broader interconnected system, undergoes decoherence and thus appears entirely alive or completely dead. This prompts another vital question. What precisely qualifies as an observer? According to the Copenhagen approach, wave function collapse results from measurement or observation, but this evokes deep philosophical inquiries. Must a conscious observer be involved? Or does any physical interaction, even without awareness, suffice to collapse the wave? Alternative viewpoints like the many worlds interpretation suggest that every possible quantum result actually materializes, each within its own branching universe. Thus, in this multiverse model, one world contains a living cat, while another contains a dead one. The observer doesn't collapse the wave function, rather, they simply become part of the version corresponding to one result, while other possibilities unfold in parallel dimensions. Still, other frameworks, such as objective collapse theories, propose that wave functions don't require observation to collapse. Instead, they undergo spontaneous reduction when they reach a certain scale of complexity or mass. Under such theories, the cat remains in a blended state until physical conditions independently force a singular outcome. Some scientists hypothesize a fundamental, yet unidentified mechanism behind wave function collapse, one that doesn't rely on any form of observation or measurement. The Schrödinger cat puzzle provokes essential questions about what it means for a system to exist in dual conditions. How can we bridge the probabilistic realm of quantum events with the concrete reality of daily life, where everything appears stable and clearly defined? Is the universe ultimately random, or are there hidden laws underpinning the uncertainty? This thought experiment also illuminates the ongoing challenge of uniting classical and quantum frameworks. Why do cats, chairs, and planets conform to classical physics, while subatomic particles follow quantum laws? The border between these realms remains a major area of inquiry, with physicists studying how classical behavior might naturally emerge from quantum origins. This effort has led to compelling research into phenomena like quantum to classical transition zones and how decoherence manifests in the macroscopic world. The Schrödinger's cat scenario has notable relevance in the realm of quantum computing as well. These cutting-edge machines exploit quantum properties, particularly superposition and entanglement, to vastly outperform traditional computers. Quantum bits qubits, for example, can simultaneously exist as 0 and 1, allowing computations on multiple fronts at once. Yet, just like in the cat paradox, these quantum computers must rely on wave function collapse when a calculation is finalized and measured. Gaining insight into how and when this collapse takes place is essential for enhancing the accuracy and durability of quantum processing systems. While Schrödinger originally devised his cat analogy as a critique of quantum orthodoxy, it has evolved into a pivotal tool in quantum thought. It forces us to question the limits of human intuition, to reevaluate our concepts of reality, perception, and measurement. It vividly exposes the radical contrast between the familiar, everyday world and the perplexing domain of quantum mechanics, where objects can embody multiple possibilities and where observation appears to influence existence itself. The cat-in-the-box metaphor remains a powerful conceptual device, illuminating the nuances of superposition, the ambiguities of wave function collapse, and the mysterious role observers play in shaping quantum reality. Though it might seem like science fiction, it urges us to challenge the most basic beliefs we hold about what is real, making it one of the most enduring and thought-provoking ideas in all of modern science. The quantum coin toss. Understanding superposition. Picture yourself tossing a coin. In our everyday world, this coin ends up showing either heads or tails. But within the quantum realm, particles can inhabit a state known as superposition, where they simultaneously exist as both heads and tails until the moment they are observed. This isn't just a lack of knowledge about the outcome. The particle genuinely resides in multiple configurations at once. This strange property upends classical thinking and reshapes our grasp of reality. To comprehend superposition, one must first embrace the probabilistic essence of the quantum world. Classical physics rests on predictability. Know the starting conditions of an object, and its future can be precisely mapped. For example, a ball tossed in the air will follow a calculable trajectory. Quantum physics, on the other hand, operates differently. Particles like photons and electrons do not trace definite paths. Their behavior is defined by a wave function, a mathematical entity that embodies all potential states the particle might occupy. When a particle is said to be in superposition, it means that its wave function includes multiple states at once. A legendary thought experiment capturing this idea is Schrödinger's cat. In this scenario, a cat is sealed inside a box with a vial of poison, which is released only if a quantum particle inside decays. Since the decay is governed by superposition, the particle exists in both decayed and undecayed states. As a result, until someone checks, the cat is simultaneously alive and dead. Though surreal, this highlights how superposition, when applied to larger systems, leads to paradoxes. The concept of superposition emerged in the early 1900s as scientists explored particle behavior on atomic and subatomic levels. Experiments like the double-slit experiment showed that light and electrons exhibited interference, something only waves could do. When electrons are sent one by one through two slits, they form an interference pattern on a screen. This only makes sense if each particle traveled through both slits at the same time. An an outcome only possible via superposition. Superposition is not merely theoretical, it has been confirmed through numerous experiments. For instance, in 2010, researchers at the University of California succeeded in placing a minuscule, visible object, a small metal paddle, into a superposed state. Though smaller than a cat, the object was visible to the naked eye, indicating that superposition might extend beyond the microscopic scale, approaching the boundary between the quantum and classical worlds. But what occurs when a superposition is measured? This leads to one of the deepest mysteries in quantum theory. According to the Copenhagen interpretation, measurement forces the wave function to collapse, compelling the particle to adopt a specific state. Prior to observation, it exists within a spread of probabilities. Observation then crystallizes a single outcome. This raises fundamental questions. What qualifies as a measurement? Does consciousness play a role? Or can mere interaction with the environment cause collapse? These questions are not just philosophical, they have practical consequences, particularly in quantum computing. Quantum computers utilize qubits, which can exist in a superposition of 0 and 1, unlike classical bits, which are restricted to one or the other. This allows quantum computers to perform many calculations at once, offering remarkable speed for specific tasks. Superposition, for example, enables quantum algorithms to factor large numbers and search data far faster than classical approaches. Superposition also plays a critical role in quantum cryptography. In protocols like quantum key distribution, the quantum states of particles existing in superposition are used to encode messages. Any attempt to intercept the message causes the superposition to collapse, revealing the tampering and ensuring secure communication. Interestingly, superposition is being explored in quantum biology. Some scientists believe biological processes such as photosynthesis and avian navigation utilize quantum effects. In photosynthesis, superposition might help energy move efficiently through a plant's light-absorbing molecules by simultaneously exploring all possible routes. Likewise, certain birds may detect the Earth's magnetic field using quantum effects in their vision systems. Still, superposition raises puzzles. Why don't we encounter this phenomenon in our daily lives? The likely answer is decoherence. When quantum systems interact with their environment, their superposed states become entangled with countless particles around them. This interaction effectively washes out the superposition, making it unobservable on macroscopic scales. Decoherence explains why quantum behaviors remain hidden in large objects. Why, for instance, Schrödinger's cat wouldn't actually be alive and dead in real life. Alternatively, the many worlds interpretation offers a radically different view. It suggests that every quantum event spawns a new universe for every possible outcome. In this model, Schrödinger's cat is alive in one universe and dead in another. This view sidesteps wave function collapse, but implies an unimaginable number of parallel realities, each corresponding to every possible outcome of every quantum event. Quantum superposition also intersects with deep philosophical inquiries. Is the quantum world truly random, or are there hidden variables maintaining determinism behind the scenes? This debate influences questions of causality, free will, and the structure of reality itself. In cosmology, superposition provides insights into the early universe. It is believed that the universe once existed in a superposition of quantum states, with quantum fluctuations guiding its development. These fluctuations left marks on the cosmic microwave background, influencing the large-scale structure we observe today. Studying superposition in this context could unlock secrets about the origins of the universe and the nature of space-time itself. The counterintuitive essence of superposition pushes us to transcend classical perspectives. It challenges our assumptions that objects possess definite attributes, that time moves linearly, and that reality stands apart from observation. By accepting the strangeness of superposition, we gain a deeper appreciation for the complexity of the cosmos.
Ultimately, quantum superposition is not just a technical term, it's a window into the universe's enigmatic workings and a reflection of the limits of our perception. It reveals a reality where particles can dwell in many states at once, where observation shapes existence, and where clarity gives way to probability. This principle not only drives forward scientific progress, it also invites wonder, curiosity, and a more profound understanding of existence itself.
The dual nature of light and matter. The phenomenon known as wave-particle duality stands as one of the most intriguing and paradoxical principles in modern physics, overturning our everyday perceptions of the universe. Consider sunlight filtering into a room. It appears continuous, smooth, and warming. Yet under scientific scrutiny, it reveals an astonishing duality. Light behaves both like a wave and like a particle, contingent on how we examine it. This dual characteristic, although simple in expression, has become a foundational element of quantum theory, dramatically altering our conceptualization of reality. To fully appreciate the significance of wave-particle duality, we must trace its historical roots. For centuries, the true nature of light was hotly contested. In the 1600s, Isaac Newton argued that light was made of tiny particles, or corpuscles, explaining behaviors like reflection and refraction. At the same time, Dutch physicist Christian Huygens offered an alternative, that light was a wave, which could bend around objects and exhibit interference. Both theories had experimental backing, but neither could fully account for all aspects of light's behavior. The early 1800s brought a breakthrough. Thomas Young's famous double-slit experiment provided strong support for the wave theory. When light passed through two narrow slits and hit a screen, it formed a pattern of alternating bright and dark bands, an interference pattern typical of waves. This result was difficult to reconcile with a purely particle-based model, and the wave perspective prevailed, at least for a while. However, the 20th century ushered in a new revolution. In 1905, Albert Einstein published a landmark paper on the photoelectric effect. He observed that when light strikes a metal surface, it can knock electrons loose, but only if the light's frequency is high enough, regardless of its brightness. To explain this, Einstein suggested that light consists of discrete packets of energy called photons. Each photon's energy was tied to its frequency by the formula E equals hf, with h representing Planck's constant. This particle-like explanation of light earned Einstein the Nobel Prize in 1921 and reignited the debate. Light must also be a particle. Yet quantum theory didn't stop with light. As the field evolved, scientists uncovered evidence that particles like electrons, long believed to be point-like and solid, could also exhibit wave-like properties. This idea was crystallized in Louis de Broglie's hypothesis, which proposed that matter particles have wavelengths inversely related to their momentum. In 1927, Clinton Davison and Lester Germer confirmed this when they demonstrated that electrons, when directed through a crystal, produced diffraction patterns much like waves. To better understand this duality, picture ripples spreading across water after a stone is dropped. These ripples have wave properties. They can interfere, diffract, and reflect. Now think of the stone itself, localized and compact, much like a particle. Quantum entities, such as electrons and photons, seem to embody both forms. They can behave like ripples or like stones, depending on how we examine them. But intriguingly, they never exhibit both properties simultaneously in a single observation. This reveals a crucial aspect of quantum physics, the role of measurement. When a particle is observed, its wave-like probability cloud appears to collapse, manifesting as a localized point. When left unobserved, it exists as a wave function, a spread of potential outcomes rather than a single value. This isn't a shortcoming of our tools or knowledge, it's a fundamental feature of reality at the quantum level. The mystery deepens with the modern double-slit experiment conducted using individual particles. When electrons are fired one at a time through two slits without observation, an interference pattern still forms, indicating wave-like self-interference. But if detectors are placed to determine which slit each electron passes through, the pattern vanishes. Electrons now behave like distinct particles. This result emphasizes the profound impact of observation and measurement in determining quantum outcomes. The consequences of wave-particle duality ripple through various domains of science. In quantum computing, for instance, the principle of superposition, a direct result of wave-like behavior, enables qubits to hold multiple states at once, allowing complex computations that outstrip traditional computing power. In cosmology, duality helps explain phenomena such as the cosmic microwave background radiation and early universe particle behavior. Philosophically, wave-particle duality calls into question our classical understanding of determinism and reality itself. It implies that, at the most fundamental level, the universe is not a collection of fixed objects, but rather an interwoven matrix of probabilities and possibilities. The duality forces us to reject simplistic either-or thinking, wave or particle, and instead accept a subtler, richer view of existence. It also brings attention to the limitations of human perception. Our day-to-day experiences are grounded in classical mechanics, where objects have defined properties and predictable behaviors. But quantum theory operates in a domain where certainties vanish and objects exist in indeterminate states until observed. This disconnect reveals that our instincts, shaped by the macroscopic world, are poorly equipped to grasp the quantum landscape. Despite its foundational status, wave-particle duality remains a subject of lively scientific inquiry and philosophical debate. Competing interpretations of quantum mechanics offer different views on its meaning. The Copenhagen interpretation embraces the probabilistic nature of quantum theory and posits that wave functions collapse during observation. In contrast, the many worlds interpretation suggests that all outcomes happen simultaneously in parallel universes, removing the need for collapse. Still other interpretations, like Bohmian mechanics, propose hidden variables to restore a deterministic view while preserving the dual behavior of particles. Wave-particle duality also intersects with efforts to unify quantum mechanics and general relativity. While quantum physics governs the subatomic scale, relativity describes massive objects and the fabric of space-time. Merging these theories into a cohesive framework remains one of science's greatest challenges, and understanding duality might offer critical insights. In conclusion, wave-particle duality is more than just a scientific insight. It is a profound philosophical revelation. It teaches us that the universe defies rigid categorization and that understanding it demands intellectual humility and creative exploration. As we continue to explore this enigmatic principle, we move closer to unlocking the deeper secrets of existence, one quantum ripple and one particle-like event at a time. The enigma of quantum indeterminacy. Quantum indeterminacy stands as one of the most profound yet frequently misinterpreted ideas in physics. It poses a direct challenge to traditional understandings of reality and compels us to reconsider the very structure of existence. At its essence, this concept asserts that, on the quantum scale, the behavior of nature is fundamentally governed by probability. This is not due to flawed instruments or limitations in our observational capabilities. It reflects a core characteristic of how the universe operates. To comprehend quantum indeterminacy, imagine you're attempting to simultaneously determine a car's exact location and velocity on a highway. In classical physics, this task is routine. You can easily record both values and use them to accurately predict the car's future position. However, if that car were a quantum object, the act of measuring its location with greater accuracy would directly reduce how precisely you could know its speed, and vice versa. This intrinsic limitation is articulated in Werner Heisenberg's uncertainty principle, a foundational element of quantum theory. Contrary to common belief, This principle isn't about flawed instruments. It's rooted in the nature of reality itself. The very process of observation in quantum mechanics alters the state of the system being measured. In the realm of classical physics, you can illuminate an object without affecting its motion. In contrast, in the quantum world, observing a particle typically involves interacting with photons or other particles, interactions that unavoidably disturb the particle's condition. Visualize trying to detect a small marble in a pitch-black room by bouncing tennis balls off it. Each bounce moves the marble, making it impossible to ascertain both its precise location and movement at the same time. Though not perfect, this analogy conveys the fundamental trade-off. As precision in knowing one property increases, clarity in the other diminishes. At first glance, this uncertainty may appear to be a minor technicality relevant only to physicists studying atoms, yet its consequences are far-reaching, fundamentally disrupting the Newtonian idea of a predictable clockwork universe. According to classical thought, if the exact position and momentum of every particle were known, one could predict the future with flawless accuracy, an idea known as Laplace's determinism. However, quantum uncertainty directly contradicts this view. The quantum realm is not deterministic, but rather governed by probabilities and mathematical constructs known as wave functions. A wave function provides a mathematical representation of a quantum system, encapsulating the probabilities of different possible outcomes. When not directly observed, a particle described by a wave function doesn't possess a single defined state. For example, an electron orbiting an atom doesn't have one specific position. It exists as a probabilistic cloud, a region indicating where it's likely to be located. This is not a matter of missing information, but reflects a core feature of quantum existence. The mystery deepens when measurement is introduced. Before observation, particles exist in a superposition, a blend of all possible states. Once measured, this superposition collapses to one specific result. So measuring an electron's position causes the wave function to shrink into a definite location, erasing all other alternatives. But what drives this collapse? Why does measurement cause it? These are among the most perplexing questions in quantum physics. Quantum indeterminacy also has significant consequences for our grasp of energy and time. Much like the uncertainty between position and momentum, there's an analogous principle governing energy and time. This relationship permits temporary deviations from the conservation of energy, giving rise to so-called virtual particles, ephemeral entities that flicker in and out of existence. Though they vanish quickly, their influence is measurable, as demonstrated by the Casimir effect, in which two neutral plates in a vacuum are drawn together due to the vacuum's quantum fluctuations. The reach of quantum uncertainty stretches well beyond theoretical labs. It plays a vital role in maintaining atomic stability. Without it, electrons would spiral into atomic nuclei, as classical mechanics would suggest. But the inherent blur in an electron's momentum prevents this, maintaining the structure of matter. Furthermore, quantum indeterminacy challenges our conceptions of causality and locality. In classical systems, causes lead to effects, and interactions are confined to nearby spaces. However, in quantum mechanics, particles can become entangled, forming connections in which their states remain intertwined no matter the distance between them. This phenomenon, known as quantum entanglement, doesn't contradict the uncertainty principle, it complements it, demonstrating that quantum laws differ radically from classical expectations. Quantum indeterminacy also forms the backbone of cutting-edge technologies. Quantum cryptography, for instance, utilizes the inherent unpredictability of quantum systems to ensure secure communication. Any interference with a quantum channel alters its state, thereby exposing eavesdropping attempts. Similarly, quantum computing exploits the probabilistic behavior of particles to perform calculations beyond the capabilities of classical machines. These computers use qubits, which, unlike traditional bits that are either 0 or 1, can exist in a mixture of states, enabling immense processing power. Still, quantum systems are vulnerable to errors caused by environmental noise, necessitating a sophisticated understanding of both classical and quantum information theory to achieve reliable performance. Despite technological triumphs, quantum uncertainty provokes deep philosophical dilemmas. If the universe's foundation is probabilistic, what does that imply for concepts like free will and causal determinism? Are observed outcomes genuinely random, or might there be undiscovered variables shaping reality? These questions echo through the annals of physics, from Einstein's famous objection that God does not play dice, to modern debates about the interpretation of quantum mechanics. Among the prevailing schools of thought is the Copenhagen interpretation, which accepts the probabilistic essence of quantum mechanics and treats the wave function as a complete description of a system. Contrasting this is the many worlds interpretation, which posits that all possible outcomes occur in parallel universes, with each observer experiencing only one. Another alternative, Bohmian mechanics, reintroduces hidden variables to recover determinism, though doing so often requires sacrificing locality. Quantum uncertainty also resonates with our understanding of chaos and complexity in larger systems. While classical chaos theory deals with deterministic systems that are extremely sensitive to starting conditions, quantum mechanics introduces an extra layer of unpredictability. This interplay between chaos and quantum uncertainty influences everything from turbulent weather patterns to the intricate behaviors of molecules, revealing that quantum laws ripple into the macro world in surprising and impactful ways. Ultimately, quantum uncertainty is far more than a mathematical oddity or a rule for subatomic particles. It offers a glimpse into the underlying nature of reality. It depicts a universe that is fluid rather than fixed, probabilistic rather than predetermined, where what we observe is shaped by the act of observation itself. This perspective not only propels scientific advancement, but also invites us to marvel at the mysterious and elegant universe we inhabit, governed by laws that both defy intuition and deepen our sense of wonder.
Decoding the language of reality, the power of information. Theory. Information theory is a hidden force that silently governs the digital age, yet its foundational ideas are frequently misunderstood or go unnoticed. At its essence, it investigates how knowledge is quantified, conveyed, and interpreted within a cosmos shaped by disorder and intricacy. Though often seen as theoretical, information theory supports systems ranging from internet infrastructure and telecommunications to molecular biology and quantum mechanics. To truly appreciate its power is to glimpse the underlying logic of the universe itself. Picture playing a game of 20 questions. The premise is straightforward. One person thinks of an item, and you deduce it by asking a sequence of yes or no questions. Every question you pose eliminates incorrect options, reducing the field of potential answers. The fewer questions you ask, the more efficiently you extract meaningful information. This simple game embodies the core of information theory, the measurement of uncertainty, and the efficient transmission of knowledge. In the mid-1900s, Claude Shannon, often credited as the originator of modern information theory, formalized this discipline. While working at Bell Labs to enhance communication technologies like telephone lines, Shannon discovered that the real challenge wasn't just signal distortion, but the uncertainty built into the communication process itself. His revolutionary 1948 publication, A Mathematical Theory of Communication, introduced the concept of information entropy, a metric for the randomness or unpredictability of a message. Greater entropy means more complexity and higher uncertainty. For example, take the act of flipping a coin. A fair coin with equal chances of landing heads or tails produces 1 bit of information per flip, a term Shannon invented. A bit signifies the smallest possible informational unit, representing a binary decision. If a coin is biased and lands on heads 90% of the time, the outcome becomes more foreseeable, and each flip holds less informational value. This helps explain why a random jumble of letters carries more entropy and requires more data to encode than a structured English sentence. Information theory extends well beyond coin tosses. It examines how effectively messages are encoded and how much can be transmitted through imperfect or noisy communication channels. One of Shannon's major insights was that every system for transferring information has a maximum threshold for accurate transmission. This is the channel capacity. Consider a crackling phone line. The channel's limit dictates how much of your message can pass through without being distorted. Shannon proved that by smartly encoding the message, one could nearly reach this threshold, paving the way for modern error correction techniques used in CDs, wireless systems, and satellite networks. What makes information theory truly remarkable is its universal relevance. Its principles not only apply to man-made communication systems, but also extend to natural biological processes. For instance, DNA can be viewed as a biological transmission channel, encoding, storing, and decoding genetic instructions. The DNA double helix contains all the information needed to create proteins, doing so with astounding efficiency. Errors or mutations, comparable to signal interference, introduce genetic variations that fuel evolutionary change. Information theory allows biologists to evaluate the precision and intricacy of these biological codes, revealing insights into inheritance, genetic disorders, and molecular functions. In neuroscience, information theory illuminates how our brains handle sensory input. Our eyes, ears, and skin are constantly bombarded with signals, light, sound, touch, which our brains must interpret. For example, the retina acts like a smart filter, condensing massive amounts of visual input into streamlined data relayed to the brain. This is similar to how digital files are compressed by removing superfluous data, like in JPEG images or MP4 videos, allowing us to store and transmit media more efficiently. Perhaps one of the most captivating areas where information theory shines is in interpreting the very nature of the cosmos. Some theoretical physicists propose that the universe might function as a vast informational system where laws of nature resemble encoded rules, and space-time serves as a medium through which data flows. This framework is especially relevant in quantum physics, where quantum information defies classical concepts of cause and locality. Quantum entanglement, for instance, can be seen as a unique kind of information exchange between particles, occurring instantaneously across great distances, violating traditional boundaries of space and time. Moreover, information theory highlights the boundaries of what can be known. In quantum mechanics, Heisenberg's uncertainty principle, stating that we cannot simultaneously know a particle's position and momentum with absolute precision, can be interpreted as an information constraint. It implies an intrinsic limit to how much we can know about certain properties at the same time. In a similar vein, chaos theory in classical systems shows how even minuscule inaccuracies in initial conditions can snowball, rendering long-term predictions unreliable, even when governed by deterministic laws. This again underlines the interplay between uncertainty, knowledge, and information. Another profound insight from information theory lies in its relationship with entropy from thermodynamics. At first, thermodynamic entropy, describing disorder in physical systems, and informational entropy, quantifying unpredictability, might appear disconnected, but they're fundamentally linked. In the 19th century, physicist Ludwig Boltzmann connected entropy to the number of microscopic states that correspond to a given macroscopic outcome. Shannon extended this to information systems, showing that entropy represents the amount of unknown data within a system. This fusion of physical and informational entropy has far-reaching implications, including for our understanding of time. As entropy increases, it aligns with the forward direction of time, the arrow that defines our experience of temporal progression. In today's digital landscape, information theory forms the backbone of transformative technologies. The internet, for instance, relies on encoding and decoding rules that transmit huge volumes of data seamlessly. From video calls to social media and machine learning, many of these systems are built upon concepts Shannon first developed. Compression methods such as JPEG for images or MP3 for sound make data transmission more efficient by stripping away redundancy without compromising quality. These techniques reflect the delicate balance between efficiency and data integrity that lies at the heart of information theory. Despite its foundational status, information theory continues to evolve. Modern researchers are applying its ideas to cutting-edge fields like quantum computing, where data is stored in quantum bits, qubits, which differ radically from classical bits. Qubits can exist in multiple states at once due to quantum superposition, giving them enormous computational potential. But these systems are also fragile, prone to interference, and require sophisticated error correction rooted in both classical and quantum information theory. As our understanding of information deepens, one insight becomes ever clearer. Information is not merely a tool for improving technology or communication, it is an elemental feature of existence itself. It links disciplines from physics and biology to consciousness and computation. Whether in the strands of DNA or the algorithms propelling interstellar probes, information sculpts our world in both visible and invisible ways. At its heart, information theory reveals something profoundly simple yet transformative. The universe may not just contain information, it may be information. A grand dialogue is unfolding, and we are participants in its ongoing exchange.
The temporal flow, decoding the direction of time. Time's forward progression is a thread that stitches the cosmos together, yet its unwavering march, the directional flow of time, remains among the greatest puzzles in science. Beyond its link to thermodynamics and entropy, this temporal flow prompts profound inquiries. Is time a constructed perception? Can it move in reverse? And why does it influence not only the physical universe, but also our memories, decisions, and the narratives we use to give our lives meaning? This temporal current isn't confined to scientific principles. It defines our very sense of existence. Our understanding of time is intrinsically tied to our capacity for memory. Recalling events involves storing and retrieving networks of neural patterns that encode previous experiences. This neural activity, along with the energy expended to retrieve it, leads to an increase in entropy, both within the brain and its external environment, in accordance with the second law of thermodynamics. However, the implications extend further. We cannot recall future occurrences because memory formation is built on sequences of causality, which inherently follow time's forward path. Fascinatingly, some neuroscientists suggest that our brains may harness entropy to navigate uncertainty. When we anticipate outcomes or plan ahead, our minds simulate various scenarios, probable configurations with increasing entropy, offering a tool for decision-making grounded in a one-way flow from past to future. This fusion of foresight and memory grants us a directional understanding of time. In quantum physics, the temporal flow becomes less clear. The foundational formulas of quantum theory are symmetric with respect to time. They remain valid whether moving forward or backward. Yet studies on quantum entanglement and the loss of coherence offer clues. When quantum entities interact, their states become entangled, evolving jointly. In systems with numerous particles, interaction with their environment degrades this entanglement over time, a process called decoherence. This shift from quantum behavior to classical physics gives rise to an emergent direction of time. While individual quantum particles don't experience time's flow, the macroscopic systems they compose exhibit a clear temporal directionality due to collective behavior.
From this perspective, the forward motion of time might not be fundamental, but could instead emerge from the interactions of complex systems within a turbulent quantum framework. If we imagine time as a flowing stream, then black holes act as gravitational whirlpools, distorting and bending space-time in extreme ways. Near a black hole's event horizon, time appears to slow drastically due to the intense gravitational field. To an outside observer, objects falling into a black hole seem to freeze, their descent endlessly delayed. Yet black holes don't merely distort time, they absorb information and contribute to the universe's total entropy. This interplay between gravitational phenomena, information theory, and thermodynamics sits at the core of modern physics. One of the key features of black holes is Hawking radiation, which allows them to emit energy and gradually lose mass. But this leads to a conundrum. What becomes of the information that falls into the black hole? This mystery, known as the black hole information paradox, hints at a deep relationship between entropy, time, and the structure of reality. One speculative idea proposes that black holes might function as cosmic safes, preserving the arrow of time within their event horizons. As they evaporate, they may re-emit this information into the cosmos, potentially resetting entropy in ways not yet understood.
Is it possible for the direction of time to reverse? Some cosmological models suggest that in a cyclic universe, where the cosmos undergoes repeated phases of expansion and contraction, time might move in reverse during the collapsing stage. In such a phase, entropy would diminish, and the temporal direction would flip. This concept opens up strange scenarios. Memories could unravel, extinguished stars might reignite, and broken glass might reassemble. In some speculative multiverse frameworks, time could flow differently across alternate universes. In certain realms, entropy might rise and fall in cycles, creating isolated domains where time runs in the opposite direction. Although these theories are highly speculative, they challenge us to reconsider time not as an immutable constant, but as a contextual property influenced by physical conditions. Beyond physics, time's directional nature is central to how we interpret our lives. We use calendars, clocks, and timekeeping systems to structure our routines. Cultural notions like advancement, development, and legacy, all crucial to the human experience, are intimately linked to time's unidirectional flow. Without this temporal progression, there would be no history and no way to plan for what lies ahead. Scientifically, time's direction is vital for understanding causation. If time could reverse, cause and effect relationships would disintegrate, making it impossible to predict or explain outcomes. The temporal flow ensures a sequence of events that cannot be undone. Past patterns can never perfectly recur. Even if the ultimate trajectory of time leads to a state of thermodynamic equilibrium, often called the heat death of the universe, where all energy is uniformly spread and activity ceases, it is this very path that enables the rise of complexity. It fuels the processes behind star formation, evolution, and the development of civilizations. Time's forward movement allows everything from subatomic interactions to galactic evolution to unfold. It acts as a unifying element across all scales of existence. Time is not merely a backdrop in which events happen, it is the underlying framework through which the narrative of the cosmos is constructed. Entropy, as the guiding principle, shapes this narrative and drives it forward. The nature of entropy. A deeper look into order, energy, and time. Entropy is often misinterpreted, despite being a fundamental principle in physics that governs phenomena from cosmic dynamics to daily occurrences. Ask someone what it means, and they might vaguely describe it as chaos or disorder. Yet entropy is much more intricate. It's about how energy behaves, how information is structured, and how time irreversibly progresses. Let's begin with a mental scenario. Imagine a finely sculpted sand castle on the shoreline. Every grain is intentionally placed to form elegant spires and archways. When ocean waves wash over it, the grains disperse, becoming part of the surrounding beach, indistinguishable from the rest. The structured form vanishes, replaced by an unorganized spread of particles. This transformation, from an organized state to one of increased randomness, captures the core idea of entropy. But entropy isn't simply synonymous with messiness. It fundamentally concerns the number of possible ways a system can be arranged. A sandcastle has a specific configuration, whereas scattered grains can be organized in nearly infinite patterns. The more potential arrangements there are, the greater the entropy. In the late 1800s, physicist Ludwig Boltzmann provided a mathematical framework for entropy. He showed that it quantifies how many microscopic setups correspond to a system's large-scale state. Take a gas inside a container. It can maintain the same pressure and temperature while its molecules rearrange in countless combinations. Similarly, a deck of cards in perfect sequence has fewer configurations than one that's been thoroughly shuffled. Thus, the shuffled deck exhibits higher entropy. This concept leads directly to the second law of thermodynamics, a foundational scientific principle. It states that in a closed system, entropy will either remain unchanged or increase over time. This explains why a hot beverage cools down rather than warming up spontaneously. Thermal energy disperses into the environment, raising the system's overall entropy. The law implies that physical processes naturally evolve toward states with greater entropy because such states are statistically more likely. Entropy is not merely about increasing disorder, it's a driving force behind natural phenomena. For example, the nuclear reactions in the sun fuse hydrogen atoms into helium, releasing energy that radiates through space. This dispersion of energy raises the entropy of the universe and enables life on Earth by powering photosynthesis. Without this ever-growing entropy, life as we know it could not exist. A frequent misunderstanding is to think of entropy purely as a descent into chaos. Though high entropy states often appear more disorganized, they are fundamentally about how energy spreads and how likely various outcomes are. A broken glass on the floor has more entropy than an intact one because there are vastly more ways for its pieces to be scattered than to stay whole. Entropy also defines the direction of time. Watching a glass shatter clearly indicates whether a video is playing forward or in reverse. That's because entropy increases in only one temporal direction. The fundamental laws of physics don't inherently favor past or future, they are time-symmetric. Yet, entropy gives rise to the arrow of time we experience, a one-way journey from past to future. Entropy affects everyday life in subtle but consistent ways. Making a bed or tidying up reduces disorder in one place, but uses energy, increasing entropy elsewhere. Cooking breakfast, for example, involves burning fuel or electricity, and the heat that escapes adds to the overall entropy of the environment. This is why technology faces limits. No engine can operate at 100% efficiency because some energy is inevitably lost as unusable heat. Although living beings seem to resist entropy by forming complex and organized systems, they do not violate this law. Organisms maintain order by absorbing energy and matter from their surroundings and expelling waste and heat. Humans, for instance, eat food to build and sustain their bodies, but release energy and entropy in the process. Life doesn't defy the second law, it functions within it.
Even the act of thinking illustrates entropy at work. When solving a problem, the mind explores many potential combinations of thoughts before settling on a solution, similar to how systems move through probable configurations. In this way, creativity parallels the natural tendencies driven by entropy. The relationship between entropy and information theory is particularly striking. Claude Shannon demonstrated that randomness and informational content are mathematically interconnected. A book written in an unknown language may look like meaningless symbols, a high entropy system,
but to someone fluent in that language, it conveys precise information. Data compression works by removing predictable patterns, thereby lowering entropy, which highlights this connection. In the 1960s, physicist Rolf Landauer discovered that deleting data increases entropy, establishing a direct connection between computing and thermodynamics. Even erasing a digital file produces a minuscule amount of heat, illustrating that information processing follows the laws of physics. At the beginning of time, the universe emerged from the Big Bang in a state of astonishingly low entropy. Over billions of years, entropy has grown, shaping galaxies, stars, and life itself. This initial low entropy condition explains the forward movement of time and the universe's unidirectional evolution. Why the universe started in this state remains an open question in physics, with ideas ranging from rare statistical occurrences to the existence of a multiverse. Black holes exemplify entropy on the largest scales. Physicists Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy is proportional to the surface area of its event horizon, not its volume. This entropy is colossal, far surpassing that of the stars that created them. Black holes emit Hawking radiation, gradually losing mass and raising the entropy of the surrounding cosmos, eventually vanishing completely. These insights have profoundly influenced our understanding of quantum gravity, space-time, and the holographic principle, the idea that all the information in the universe might be encoded on a two-dimensional boundary. If the second law holds universally, then the cosmos is heading toward a state of ultimate entropy, a phenomenon known as heat death. In this final stage, all energy would be uniformly distributed, rendering work and structure impossible. Stars would extinguish, galaxies would drift apart, and even black holes would dissolve, leaving behind a cold, lightless expanse. Though this vision may seem bleak, it also highlights the rare and precious nature of the present, an era filled with richness, organization, and life. Entropy is more than just a concept in physics. It offers a powerful perspective on existence, guiding our understanding of energy, time, information, and the cosmos. Rather than signaling doom, entropy underscores the beauty of impermanence. It's within this delicate framework that complexity, consciousness, and meaning find their place. In the inevitable tide of change, entropy doesn't erase purpose. It provides the context in which life thrives.